especially by Microsoft, and then some standardization effort as well in hollow core fiber. So as I mentioned that there are a lot of talks about hollow core fiber in very wide details in workshops, market was tutorial, and a lot of presentations. And most of it were by the industry and the research through the industry or by marketing of the industry. So I mentioned here in the blue color all the relevant industry who actually supporting the hollow core fiber or developing the hollow core fiber. Interesting is Microsoft is the pioneer in it, but after the Microsoft, Chinese companies are way good in working in hollow core fiber, especially Lean Fiber, China Mobile, and YOFC. They are actually manufacturing the hollow core fiber. There are some fiber sensing also happening with hollow core fiber. Few of the talks were there. So now hollow core fiber gathered a lot of attention in recent years, starting from the Satya Nadella from the Microsoft, which announced that there is a 15,000 kilometer of hollow core fiber going to be deployed in next 2 years. And following that, this year, this was the news in last year, and this year the Microsoft announced that they started to deploy such network in Azure network, hollow core fiber. And then Amazon as well, Amazon AWS also started to deploy and use the hollow core fiber for their data centers. There's more effort. OFS has started to build the hollow core fiber, sort of manufacturing the hollow core fiber. Lintia, Nokia, Furukawa as well started to work on hollow core fiber or developing the solution for hollow core fiber. This another company called Relativity Networks from US. It raised some money to advance the hollow core fiber development. It worked with Prismian, a company in Netherlands, which is pioneer in manufacturing of fabrication of fiber. So to develop the hollow core fiber production facilities. So there are some news. Lean Fiber, a Chinese company who actually started to sell the hollow core fiber. They started to develop the fabrication facilities and everything. And in their website, you can see that hollow core fiber is available. Also on the Microsoft, when they acquired Luminosity, they also they started to develop or build the hollow core fiber. And OFS, in their website, they mentioned one of the product, AccuCore hollow core fiber, and they started to provide the solution in terms of fiber bundles. So AccuCore hollow core fiber white paper is also available there. So there are a lot of factors. Yeah.
This is commercially available, Ryan, right now?
This is right now commercially available, yeah.
Okay.
Commercially available, but it's expensive than regular fiber. We'll see later on in the presentation how the cost is going to reduce. So now the question comes to mind, like what is hollow core fiber, how it's different than regular fiber, what we are using right now. So regular fiber, which is single mode fiber, ITU standard at G.65 something. So regular fiber is made of core and cladding is just a glass, and core is also a glass doped with some element. So its refractive index is higher than core. Whereas hollow core fiber, it has a glass cladding, but the core is almost empty. So if the core is empty, means there is no glass. It's just air, and even sometimes the refractive index air is even very rare. So in fact, it's low density air sometime as well. So the structure is made inside the core such a way that there is a air or vacuum can be present at the core instead of glass. So that's the difference between hollow core fiber and single mode fiber. Is hollow core means there is no glass, just air in the core of the fiber. Now,
So
how it works?
How do you splice it?
Those things are here. We'll show it later. How they splice. They develop the splicing and everything. Because for the splicing, you don't need core. You need to arrange the matching the cladding and all this structure.
And the air doesn't come out.
It come out, but there is a solution for that.
Okay.
So how the light is guided through the fiber itself. For single mode fiber, you have refractive index mismatch. We know that core has a little bit higher refractive index, and so you have total internal reflection, and so light is confined inside the core of single mode fiber. For hollow core fiber, it works on a property called anti-resonant mode. So in anti-resonant mode, all this structure you see, it's create an anti-resonant at the boundary, and inside is a resonance. So because of that, if you solve the field pattern, the field is confined in the air, not outside. And that's how the light guided in the hollow core fiber. Now, if you look at the mode field diameter, the mode field diameter of hollow core fiber is bigger than single mode fiber, almost double. And because of that, the single mode fiber will provide the single mode. The hollow core provide quasi single mode, means it propagate the single mode plus some fraction of multimode as well. So if you talk about the numerical aperture is a bit higher in single mode fiber, but smaller in the hollow core fiber. Numerical aperture gives the idea that how easily light can be added or connected to the fiber. So hollow core fiber is a bit difficult, and because of that, the as the expectance angle is lower, it's very difficult to make connector for it. So that was the challenge, operational challenge in the beginning, but they tried to solve it. Now, a most important parameter is loss. So for the single mode fiber, we know that loss initially was very high in 1970s when it was developed, and recently, last 40 year back, the loss reached to 0.154 kilometer per dB per kilometer, which was the lowest loss in last 40 years. And then the loss is almost constant over recent development. In this OFC conference, they also presented the single mode fiber with ultra low loss, less than 0.14 dB per kilometer, and that's the best possible loss achieved so far for the single mode fiber in last 40 years. Whereas for the hollow core fiber, the loss is very low, less than zero point 0.1 dB per kilometer, as you can see in certain C-band range. For 0.2 dB per kilometer is very wide, and starting from the beginning of the O band or E band and up to SCLU, entire 4-5 band is covered by hollow core fiber. So loss is low and also is covering the wide band rather than a single mode fiber which cover only C or L band. This was the one of the paper they presented that hollow core fiber has a very low loss of 0.1 dB per kilometer. So lean fiber actually developed this fiber, what was in the research, and they put it into production, and they found the fiber with after the cabling and everything, less than 0.1 dB per kilometer. So if you look at the loss profile,
Could you go back? What in the L band? What about the L band?
so L band also you can see the loss is low. You see here,
Mhm.
the L
Okay,
band is less than
okay,
0.1.
okay.
So if you see the loss profile, so single mode fiber, the loss is maximum is here, 0.15. My minimum is 0.15, and the hollow core fiber loss is reducing. Now it's below 0.1, and more effort is going, so it's going to be even more lower and lower. Keeping in mind that this is the development of last 10, 15 years only, while single mode fiber developed in last 50 years. So next coming 5 years or coming decade, the loss will be even much lower. Theoretically, the loss can be 0.001 dB per kilometer possible with hollow core fiber. Now, so we have a very low loss for hollow core fiber as compared to single mode fiber. The loss mechanism is very similar to the single mode fiber. In single mode fiber, you have water absorption. Here is gas, so it's carbon dioxide absorption. Scattering, mode leakage, and bending is the very similar um, way of losing power in the hollow core fiber as compared to the single mode fiber. Now, polarization dependent loss is very low in single hollow core fiber, which is kind of an advantage because we are using dual polarization signals. So it's kind of better than single mode fiber. Bending loss is a bit higher, but not too higher. But overall, it brings a lot of benefit. For example, if you have very low loss, so you can have higher OSNR, you can have longer span, as well as you have low power consumption. You can send for the similar distance, you need to send very small power as compared to single mode fiber. The next one is nonlinearity. So if you look at the nonlinear profile,
Before that, how many mode it support? A single mode?
it's a quasi single mode, so it supports single mode plus fraction of multi-mode, but intermodal interference, which I'm going to discuss now, is very low. So it's kind of a almost single mode. Yeah,
Yeah, but I mean,
it's not two
crosstalk of
mode.
even
Yeah,
a
so
very
there.
small crosstalk is disaster.
Yeah, but I'm going to show that what is the crosstalk.
Okay, all right,
Even in the single mode, there is a crosstalk also happen, but it's very similar order.
okay.
Okay, so nonlinearity, if you look at the nonlinear performance, use in the single mode fiber, if you increase the power, performance improve, but because of the nonlinearity, it saturate and goes down. So if you send higher power in single mode fiber, the performance doesn't improve. It's reached to a saturation because of no nonlinear effect. And that nonlinear effect coming because of you have a doped glass core. In hollow core fiber, there is an air core, so nonlinearity is very low or almost zero. And because of that, if you send higher and higher power, there is no nonlinearity, so performance just keep improving. That's the benefit of hollow core fiber. That's the main benefit you can say of hollow core fiber. So you have lower nonlinear effects, means you can transmit as much higher power as possible, and then performance will be better and better. This means you can have a longer span length, more than 80 or 100 kilometer, which we're going to see on later on. In this presentation, they started to also show that one of the deployment where they show that Raman gain of a hollow core fiber is almost zero. As you can see, this is the hollow core fiber. This is the single mode fiber where I have significant Raman gain. So if Raman gain is almost zero, means you can send C plus L plus S plus U multiband together without causing problem of the nonlinearity. So both curve nonlinearity and Raman nonlinearity is very little in hollow core fiber. That's one of the main advantages.
But
So
it's
here one of
mainly,
the applications.
but it's mainly you cannot use Raman amplifiers.
Maybe you don't need it, but
maybe you don't need them. Yeah.
you don't need it. Yeah. Okay. So here is the how the span length is increased. So usually, if you have a single mode fiber, usually the span length is 80 to 100 kilometer. And in this paper, where they presented the field deployment over more than 300 kilometer without any amplifier, they use 320 kilometer link with hollow core fiber without amplifier, and it's locked. It's locked the channel, all the channels. So nonlinear in terms of data, in terms of number, nonlinear coefficient of hollow core fiber is 10 to the power -4, while here is 1 to 10. So it sees very, very little. Raman effect is almost negligible. And because of that, the bandwidth of the hollow core fibers can support up to 66 terahertz, all the possible bands. And in the terms of bidirectional properties, so single mode fiber partially support bidirectional. If they use the single mode one fiber for both directional traffic, the both direction can interact to each other through the Rayleigh backscattering, Boolean scattering, or even sometimes Raman scattering. And because of that, the single mode fiber is partially bidirectional, but hollow core fiber is truly bidirectional because there is no nonlinear effect. So you can use the single fiber for data transmission from both sides. Single fiber. So the benefit comes as a high power transmission because you don't have nonlinearity, so you can transmit very, very high power. A longer span you can transmit. You have higher capacity because of the multi-band operation possible by lower Raman effect. And then this is interesting one, the QKT, higher range of QKT. The QKT is limited by range also because of nonlinearity, because of the Raman effect can add some extra power to the QKT channel, and those can be avoided in hollow core fiber. Also, the loss is low, so QKT is better for the QKT applications. So there are some presentation were made where in OFC for example, this one using hollow core fiber for long-term solution for capacity scaling. Another one here is bidirectional transmission, as I mentioned, by this Chinese company YOFC. And then future quantum network, this is in the workshop they discuss about using hollow core fiber for quantum network, because then you have a very longer span length possible with the hollow core fiber. Now, next one is dispersion. The chromatic dispersion of the hollow core fiber is almost 3 to 4 times lower than single mode fiber, which is also an interesting one. Dispersion slope is almost zero. And the interesting one is the PMD. And this is a paper they discuss in OFC, that PMD of newly developed hollow core fiber has a very low value, 0.1 picosecond per square root kilometer. So if you compare the PMD, it's almost half of the single mode fiber. Now, this one is interesting one, intermodal interference. So because of the quasi single mode fiber, so it's more than single mode, but not exactly even two mode, a single mode from plus some fraction. So intermodal interference is less than -60 dB. For the single mode, is -70 dB per kilometer. It's also depend upon core design. So they're developing better and better core design for even lower and lower value, but it still is not too far away from the single mode fiber. And because we have a lower chromatic dispersion, so you don't need to compensate those dispersion in DSP. You don't need to compensate nonlinearity. You don't need to remove the phase errors and etc. So DSP can be very simple and lower cost, lower power consumption, etc. So the cost of the device will reduce in future if we all use hollow core fiber, and of course the higher capacity.
But usually coherent likes dispersion in terms of not
yeah.
with
But
nonlinear.
why
But there's no nonlinear here, you say.
exactly? So the single mode fiber coherent like the dispersion, but here there is no linearity, so we don't need dispersion, and it's not there both of them here, so it's better.
Okay.
For the shorter range, for example, the DCI application or for the shorter range communications, the data is limited by the dispersion, and because dispersion is lower, so there is a possibility of high capacity for lower distances as well. Now, the damage threshold is important one. Why we cannot send high power in the single mode fiber? Not only because of non-linearity, because more and more power we send through the fiber, there is a chance that at higher optical power, the glass itself can get fused. But here we have only air, so there is no problem with the fusing. So because of that, there is lower back reflection and higher damage threshold. And because of that, you have a higher power transmission limit. So for single mode fiber, only few watts can be sent, but for hollow core fiber, you can set up to 1 megawatt power. So there are certain use of it. For one of the best use for the telecom system is to deliver the electrical power in submarine network for the amplifiers. So even after 300-400 kilometers, you need amplifier in the submarine system. Usually for the electrical power, the electrical cable goes, but here we can use one of the channel to transmit very high power, high ledger power, which get converted to electrical power at the amplifier to power up the amplifier itself. So that's another application coming up. And this is one of the
there's
paper.
no eye safety laser restriction for this fiber?
There is eye safety is always will be there, right? It's because that depends upon the technician, not for the fiber. So
yeah, but usually the customer doesn't. I mean, it needs to be like 1M, so you need to have some kind of
yeah.
APR or I don't know.
Yes, but Boaz, you said what is the physical limit of the fiber? Eye safety is completely different.
Yeah, I know,
not
but it
related
comes
to fiber.
together. It comes together. I mean, if we
Yeah,
are
yes,
doing
no,
an
but
amplifier like this, you need to have some eye safety mechanism here.
yeah, I mean theoretically, what is basically the tolerance of the fiber?
No, I was wondering if there are special standardization like today for hollow core fiber
I
in terms of safety.
believe it won't change because the eye safety limit depend on the eye, not on the fiber.
Yeah, exactly. It's the same. Actually, one of the presentation they show that about eye safety. I mean, about the OSC channel. So it's the very same like what we are doing right now. It won't change.
But 1 minute, Abi, if it's such a wonderful fiber, why don't we see it in undersea application? I mean, in
Because the
undersea
cost,
application,
first of all,
the
it's
cost.
developed recently, last 10 years, and it still is under. Let's say the one of the main reason why we didn't say hollow core fiber is the loss. The loss was very high. It's more than 0.2, 0.3 dB per kilometer, and that's why people were not using it. Recently, the new companies came up with the solution, and now the loss reduced to less than 0.1 dB per kilometer. So and now they are fabricating more and more. So still the cost is high. Loss is very low than single mode fiber, but the cost is currently high. So the more the ecosystem will develop, more people will demand it. The cost will go lower, and then it will come to submarine eventually.
Yeah, and by the way, what about the interaction between the hollow core fiber and erbium doped fiber? I mean, how does this splicing
Coming up,
together? I mean, okay.
coming up. Okay, so this is one of the presentation that discuss about simultaneous delivery of power plus the data together without affecting the data. So you can see they are delivering like up to 2 to 3 kilowatt of power. Okay, so this one is latency. Another advantage is latency because it's air. So the whatever light goes, laser go, it goes travel through the speed of light in air. But in the single mode fiber, the speed is reduced by the refractive index. So it's more almost 50% faster. So there are several applications in the past. Actually, the application of hollow core fiber has started for low latency. For example, this one high frequency traders for financial system, or the British Telecom used it 2-3 years back for low latency applications in their network. So these are the initial application, but people are now not much talking about it. Still is advantageous latency issues, but now people are more talking about high capacity system in terms of hollow core fiber because the loss is reduced, not about latency. So now the real issue comes, operation challenges. So one of the challenges is splicing. So single mode fiber, we have arc fusion splicing, and hollow core fiber that develop also the arc fusion splicing as well as gluing it together. And splicing loss is a bit higher than single mode fiber, but it still is available. So device splicer itself is a bit complex, expensive, bit advanced as well as required. And there are several challenges. One of the challenges, extra challenges than single mode fiber, for example, is interface contamination. If you have interface contamination, you need to clean it properly. And then the air pressure or gas pressure changes because the fiber is broken, the gas pressure changes. Usually the pressure is maintained same as the atmospheric pressure. So there is not a huge change, but it still is changes and they need to maintain during the splicing. That's why the splicer device is very complex because it has to push up some air in the fiber while doing the splicing. That's why it's
You
very
need
expensive.
special TDR for this fiber?
Yes, you need. I'm going to discuss it soon. It's going to come. Okay, the next splicing is between the hollow core fiber and single mode fiber. Even let's say hollow core fiber comes up and it's coming up by the way, but there is a millions of kilometers of single mode fiber. We cannot reject it. So we need to integrate the hollow core fiber with the existing single mode fiber. So we need to connect as well as splice the hollow core fiber with single mode fiber. Now, hollow core fiber has a bigger mode diameter, right? And single mode fiber has a smaller. So you need to create a special splicer. So they did develop. So they actually heat up the single mode fiber at the end, increase the size of the core by a splicing device, and then fuse it together. They have anti-reflection coating to reduce the reflection. And this is how the splicing done. There are several challenges. One of them is mode match, field mismatch. There is a deformation possible. And then the contamination is also possible. So that's all in causes the extra loss, and a splice loss up to 0.3 dB is reported, but it's useful when you need to integrate with the single mode fiber. And now the connector. The connector is answer for the ADFA. Like it's still the amplifiers is the same amplifier. It's not new amplifier. So if you have an EDFA amplifier, you need a connector, and so there are several connector has been developed. Hollow core fiber to hollow core fiber connector, as well as hollow core fiber to single mode fiber connector. So hollow core fiber to single mode fiber connector, this one is used for amplifier to connect to the either to amplifier or connect to the already single mode fiber infrastructure. For example, if you need to connect to ROADM or you need to connect to another fiber, we can use this kind of connector. The losses is a bit higher, again almost double, but not too high, 0.1 dB per connection. Now, coupler and splitter is another part. So coupler splitter we need. So they developed like 2-core splitter. So actually 1:2 3 coupler. They also developed 1:4 waveguide kind of coupler splitter or coupler both together. And then it comes for OTDR.
Why do you need a splitter coupler?
You
maybe
need many
for
places
OLP.
in the lab. Yeah.
Okay.
Also,
connected to the ROADM is the regular one.
Yeah, ROADM is regular, but let's say if you are developing some protection mechanism for amplifier.
Yeah, protection. 1:2. Yeah. Okay.
Yes, but
now,
why not using the simple single mode coupler? You said
so you have extra
not...
no,
Yeah,
but then you need to use a connector and then use coupler. You are losing a lot of power.
Yeah, it's better to have there's no logic for this because it's connected to the outer plane.
And also you're going from hollow core to hollow core. Yeah. And you're going to hollow core to hollow core. So why to bring single mode?
Well, that's the question, where it goes. Usually it goes to transceiver, so it's not...
No.
Not
this is for the
protection.
This is for the OTS or OMS. It's not for for going to the ROADM, you stick with the regular one because the ROADM doesn't change.
The ROADM doesn't change. It's for protection mechanism.
But you know, sometimes you have amplifier near it, so if you have amplifier and you anyway need to go to single mode, but never mind. Okay.
Never mind. Anyway, even you don't need it in the operational part. You need it in the lab anyway.
Okay.
You do some work in the lab.
Okay.
Anyway, so OTDR is one of the challenge. Okay, so this field trials they discuss about OTDR. So usual OTDR, you just send OTDR pulse, reflect back, and you get the information, right? The fiber cut or some extra loss or something, or a splicer loss or something. But since there is no core, so you don't have a reflection. I mean, there is a reflection because of the gases, but very weak. So in order to OTDR to work, they use additional ADFA, additional alpha. After the OTDR
finally we found the use for the high power OTDR.
Exactly. This is the final use, and because there is no nonlinearity, so it doesn't affect the data channel as well. So that is the way to use OTDR, and in this this report, they demonstrated the OTDR with hollow core fiber. They use OTDR from both sides to cover the, let's say, 646 dB span loss, and then you can see the splicing here.
But
this is splicing between
how much do they amplify it? Even I mean, today the OTDR is, as we know, the problem with Axelink, it's 20 dBm pulse.
Yeah, I need to check how much they are amplified, but
Okay.
it's more than 30 dBm, something like that.
Jesus.
Yeah, because it's air, so you have back reflecting is very low.
Guys, you went to TDR. I think let's start with the amplifiers. But okay.
No, the amplifiers are the same.
Amplifiers are regular.
But for the C band, what about the other bands?
The L band amplifier is the same. And now other band, what about
understand.
you need to develop the
But
amplifier.
Now you said that the other bands are different attenuation loads. Then you need
There are low loss,
no.
But you need the amplifier. You need to develop an amplifier.
Previously,
the amplifier wouldn't help you because the loss was too high.
Yeah. No, wait. The other band, for example, if you go to S or U band, the loss remain lower than 0.2 dB per kilometer, lower, even close to 0.1 dB per kilometer. And because of that, you still need the amplifier after, let's say, 200 or 300 kilometer. But those amplifiers, they are already developing, right? Like thulium dot amplifier, they develop for S band. Similarly, thorium dot amplifier developed
VLF for the C band, and then like LF for the, I don't know, U band, something like this.
Yeah.
Okay.
The OTDR is a counter or co-propagating?
It's co-propagating. It doesn't matter, but it's co-propagating. They use, by the way, here they use both bidirectional OTDR because they have a very long length, so they need to cover entire length. So in this one,
but you can measure. But the question maybe you're measuring a counter in both sides.
No, it's not counter. It's co-propagating.
It's
co-propagating. You see here. The after edify is going with the data reflected back and through the circulator they take it out.
And it's strange because now you have a very low back reflection coefficient, but on the same way, the fiber span is now 200 kilometers.
Yeah.
It's not 80 kilometers like it used before.
Yeah.
So
that's why you see
very challenging. I think it's very challenging.
They need to cover the span length of 46 dB, which means like consider it's like 0.1 or 0.12 dB per kilometer loss. It's more than 300 kilometers. So that's it's challenging. OTDR is challenging. They have but they develop OFDR similar to OTDR in the frequency domain analysis, and they are so best application. Probably OFDR is going to replace the OTDR for this purpose. Anyway, so now come to the why we don't have a volume. So supply and cost is a chicken and egg problem. Since you have a low demand, so price is high. If demand will be high, price will be low, and so it's feed in a loop. So that's the problem. But usually the fabrication method of the hollow core fiber is very similar to single mode fiber with some differences. Single mode fiber right now can develop up to 15,000 kilometers per preform. This is a preform they develop. And then, the drawing table, they need to draw the fiber from preform. So right now it's a very high, 15,000 kilometers per preform for single mode fiber. For hollow core fiber, it maximum so far is 200 kilometers per preform. And these methods are keep developing. And lean fiber, OFS are leading this. Corning is also working in this. Corning also had some presentation in this area. So the question is how and when we can reach from this number 200 kilometer per preform to up to at least 10,000 kilometer per preform. Then the price will also reduce and volume production will be possible. To understand that, we need to see that how the single mode fiber developed. Single mode fiber took like 50 years to come to the number of 10,000 kilometer per preform. So this is here. It's over here.
No, the problem with the hollow fiber is not its cost or when it will be available. The problem is the installation cost. Installation of new fiber is $billions. The price of the equipment is negligible to the price of installation. That's why
I think it's the operation issue.
No, 1 minute. Yeah. This is why I ask about undersea operation, because in undersea, every time it's a new cable. Okay, they don't use the same cable. Every time they have a new project, they put in the ocean a new cable. So the first candidate is the undersea transmission.
So
they
And
are
it's
doing
claimed
it.
that
Mal,
But
yeah,
it's not
I
So
don't
used
this
by
want
the
is
to
undersea.
steal. Yeah, don't want to steal time from Abhishek lecture, but just a
Yes, yes.
remark. We are seeing networks where part of it is installing. You're right that it costs a lot of money. Okay, you're 100% right. But there are places where people are installing new fiber. It's not like it's not happening. It's happening. Okay, so again, it's not a big numbers, but we see new fibers that people are digging when they don't have fiber. So once this technology will be valid and cost effective enough, then somebody will need to decide, is he putting a standard cable or this one? And this is something that you cannot say that nobody will put new fibers. No, this is not true because
No,
it's
but
happening right now.
first of all, we need to wait to the undersea application.
No, no, no.
And
Leave the
Yeah,
under.
yeah, this is what Microsoft announced to use 15,000 kilometer of undersea cables. So it's already a starting. The ecosystem, as Rafi said, it will take time. A new fiber are installing every year. Few millions of kilometers are installing every year. But now it's depend upon the ecosystem. We don't need a new equipment for hollow core fiber. We need only new fiber. The fiber cost is high. Equipment cost is same what it was before. So it's just a matter of hollow core fiber cost is reduced, ecosystem is
yeah,
properly to develop, so people recognize that okay, this is a benefit,
i-
and
it's
some
better than the
starting
multi-core.
is better than
Multi-core
multi-core,
you need, yeah.
definitely.
Multi-core is more complex. And
You
Google
need a
went for
special
multi-core.
ADFR,
Yeah, yeah,
yeah, multi-core require a special ADFR, a special ROADM, everything.
yeah,
Here it doesn't require anything special.
yeah.
So it's
This
already a
is much more
starting.
interesting. I agree.
Yeah, already a starting. Microsoft already announced. Amazon is doing it. It will take time. Maybe next 5 years you'll see more field deployment of it. So anyway, the cost. That's what I'm trying to mention, that the cost will reduce when the manufacturing will be more and more foundry are getting involved into
By,
developing hollow core fiber.
by the way, just for your information, I got
Yeah,
questions from Barty last
yeah.
week whether we are investing in developing hollow core fiber. I
So
mean,
here
so
is the answer.
it started, let's say.
It
It's
started. Yeah.
starting, yeah,
So,
it's
so you
starting.
said hollow what?
No, I didn't say hollow what. I said we are
Okay.
waiting for the ecosystem to ramp up.
Yeah.
But
Tell him we are doing Holocaust fiber.
Guys, I have
I
only
told
20
him
minutes. I need to cover two more topics. So
okay, please
I told
go.
him I'm concentrating in the hollow point bullets. Never mind.
okay, I will just go quickly. So one of the another benefit I just wanted to show that. So here the net. This is one other workshop where they discuss about network provider viewpoint, and this presentation was from the Sienna. And they discuss that hollow core fiber, of course, is like can be compatible with a splicer and connector with single mode fiber, so it can be easily integrated with the existing system. Plus, it's high capacity beyond C plus L, what we have seen. And one of the interesting thing, because you have low loss and you have you can go very long distances and you can transmit as much high power as possible without caring about nonlinearity, means you can literally develop a EDFA which is high output power, so that you can go for very long length without caring about uh, nonlinearity. And if you go for a very high power, the noise figure reduce, because at the high power, the spontaneous emission noise is lesser and lesser. And so developing a high power EDFA is the next step they are thinking of, where we can go 200 times higher than the low right now, what is available EDFA power. And so nonlinearity will be more and more low from the amplifier itself. So not only we can transmit high power, we can make longer distance because without taking care of it's nonlinearity, but we have a very high output power from EDPA. So not only you can go for 400 kilometer, maybe in the future you can go 1,000 kilometer single span without amplifier or with a single amplifier. So that's the possibility they are discussing now. Um, and this is some of the consideration they talk about link budget calculation if you're integrating the single mode fiber with hollow core fiber. So PMD calculation, PDL, and modal interference, etc. There are several applications right now. So this one is low latency application, high frequency trading, financial network, etc. DCI application. But the interesting one is this one for us. So high island hopping. So if you have a single span of 300 kilometer, we always face some problem with non-linearity without amplifier, but here you can easily use it. Multiband is another application. Large span QKD, as we discussed, is another one. Submarine, people are working on it, and one of the most useful part is delivering the electrical power through the fiber itself. And the fiber sensing. Don't ask me right now how the fiber sensing is done because there is no code, but there is a nice application. I'm not discussing in this presentation, but I can discuss later on if you're interested. Some of the deployment effort I will go through quickly in 2-3 minutes. So Microsoft have shown that because of the IMI is reduced very much, so the deployment effort is increased to 4,000 kilometer, and the future in 2026 it should go to 15,000 kilometer with very low IMI. And this is one of the two deployment Microsoft has done. This is Microsoft Azure Network. One for DCI application where they use 32 hollow fiber, 48 single mode fiber, and they have a splicer. And as you can see, the splicers are here in this 2-point. They use OTDR trace to see the splicing is happening. So you can see the splicing happening there. The traffic is working very fine with hollow fiber, no traffic downtime, stable prefect bar, also stable into span loss. So overall, they try to show that with hollow fiber, the traffic is normal without causing any problem. And then this one was not for a DCI application, for sort of long haul, but it's single SFAN 300 kilometer. And there they also deployed the hollow core fiber inside the London city, inside the ground. And you can see all this splice tray and everything here in the picture. And they again have OTDR trace to see that how the splicing is happening. And then they try to calculate the fiber penalty, and you can see the back-to-back penalty. Back-to-back to the 200 transmission, there is almost no penalty because there is no linearity. There is some standardization.
What channels they were running? What rate? 800 giga? 400 giga?
No, 132 to 138 gigabaud. So they're going 800, 1200, 1.1 tera or 800.
Yeah,
gigabaud.
it was 800 giga. Yeah.
800 giga. Yeah.
Eli, it's look like with this fiber, VPI will be out of, will have no work. I mean, there's no nonlinearity, no dispersion, nothing.
So will the DSP designers.
So there's the digital twin.